So test series, whether it would be subject wise, topic wise.
Welcome to Ace Engineering Academy. I am Ravi Sir. I am the faculty of production subject in Ace Engineering Academy. Today in this session, I am going to teach you the shrinkage allowance, that is very important topic many times in the GATE examination as well as ESC examination, SSC JEE, state level examination. The number of time the questions are asked on shrinkage allowance. That's why this topic is very important, and in the 1 hour session I will explain you that topic very nicely. Now this shrinkage allowance is the topic, the chapter is metal casting from the subject, that is production engineering is the subject. Yes, production engineering is the subject. And many students know that the weightage of production subject is very high, highest weightage of production subject is there. You can see out of 100 marks, GATE exam is of 100 mark, and out of 100 mark, for GATE mechanical engineering, the weightage is around 16 marks. And for GATE production and industrial engineering, this subject has a weightage 28 marks. And in that subject, total 9 topics are there, 9 chapters are there, and out of that all 9 chapters, the casting is one of them, whose weightage for GATE mechanical engineering is 2 to 3 marks. Most of the time for 2 marks they are going to ask. For the GATE PI 4 to 5 marks, ESC prelim 1 to 2 question, and ESC mains 1 to 2 question. And many state level examination, SSC JEE, in many examination they are asking the question on casting, and especially they are asking the theory question on this topic, that is shrinkage allowance, and it is very difficult to understand. In the student there are number of confusions about that topic. That's why I selected this topic for the today's session, right? Now see the shrinkage allowance. Before that, I want to give you the introduction of casting. It is better to give the introduction of casting than it is better to start. Now see here, you can see this diagram, you can observe carefully this diagram. Here all the lines you can see that all is made up of molding sand, all is made up of molding sand, and this is the diagram of mold. This is the total diagram of mold, and this mold is made up of molding sand. What is that molding sand? I am writing here the silica sand. Silica sand. From the river we can get the silica sand. In that silica sand we can add the clay, and plus we can add the water. Then we will get molding sand. Then this is the mold made by molding sand. And this mold has the 2 parts. One part is upper one, that is known as COPE, cope. The bottom is drag. This upper portion is known as cope, and this lower portion is known as drag. And you can see that there is one line between that two, and that line you can see, you can observe it carefully. This line is there, and that line is known as parting line. That line is known as parting line. The parting line is divided this total mold into 2 parts. The upper one is cope and lower one is drag. On that questions are also asked in SSC JEE examination. A, B, C, D. How to remember that? A, B, C, D. C is cope on the top. D is A, B, C, D. After C there is D. Then it is drag. C, D. You can remember that. And in that mold only, you can see there is one basin is there, basin, and that basin is known as pouring basin. And in that pouring basin, we are pouring the molten metal. From where we get the molten metal? Just take a solid metal, put that solid metal in furnace, give the heat, and because of that, that solid metal will melt. It will convert into liquid. Melt means what? It will convert into liquid, and that liquid we have to pour in that pouring basin. We have to pour into that pouring basin. Then that liquid metal from the pouring basin will enter into the sprue. You can see that this is the sprue. Conical shaped sprue is there. That molten metal will enter into the sprue. After sprue, this part is known as runner. This horizontal part is known as runner. Then from the sprue it will enter into the runner. And after runner, this gate, this is entry point, is known as in-gate. This entry point is known as in-gate. This is the entry point from where the molten metal is entered into cavity. When that molten metal will enter into the cavity will full of molten metal and then allow it to solidify. Wait for some time. If you are going to wait for some time, then what happen? The continuously heat transfer will go on. The continuously heat transfer will go on. Continuously the heat transfer will go on and that liquid will convert into solid. And when that liquid metal is converted into solid metal, then we can break that cope and drag and we can take that casted component. Just see, the efforts are required. We need to make the drag, we need to cope, we need to make the cope, we need to make that cavity here. This cavity is what? This cavity is empty space. Now I will tell you how to make that cavity. This is also question, how to make that cavity. Yes, then whole effort is there. We have to break the cope, drag and we have to take out the casted component. Yes, now first we will see how to make that cavity, how to make here empty space. And you can see, you can observe it carefully. What is the shape of cavity? Na? The same shape of casted component we will get. The same shape of casted component we will get. Now see here. This is the pattern. What is that pattern? What I want to tell you? I want to tell you how we can make the cavity. I said that this total mold is made by molding sand. But I didn't say that how to make that cavity. And that cavity is also known as casting cavity. How to make that casting cavity? That procedure I am going to tell. For that we need the pattern. Just see, I have taken one pattern here. You can see that this is the pattern. Which material is here? By observing diagram, you can tell that this is the wood material. The pattern we can made by wood material. The pattern we can made by metal. The pattern we can made by plastic. The pattern we can made by wax, polystyrene. Many material we can use for the pattern. Out of that I used the first material, that is wood material I used. Yes, what I am going to tell? I am going to tell how to make that cavity. I am going to tell you how to make that cavity, and for that I need one pattern. Now you observe carefully the shape of pattern. You can observe that the shape of pattern you can see is the same as the shape of this cavity. It must be there. Huh? Shape of pattern and shape of cavity must be same. Okay. Now this is the wood pattern. Now see the next. I want to make the drag. I want to make the drag first. You observe it here. This is the drag. I want to make the drag first. I am making this drag here, and for that I taken that pattern, and you see that here is the pattern, and on the pattern I given the molding sand. This is total sand is known as molding sand. This total sand is molding sand. This total sand is molding sand. Hence there is one pattern. One pattern. Then on the pattern we kept molding sand. You can see that 1, 2, 3, 4. For that cubical pattern, the total vertical 4 faces are there. On the all the side also we gave some sand. Here also, here we gave sand, and we started giving the compressive forces here to get the strength to the molding sand. To get the strength of the mold, to get the strength to the drag. Here we are making the drag. I am compressing. One big question is there. When we started compressing, then what happened? The sand is going from here, going down from here. The sand is going down from here. Why it's so? Then how to make that? Just say simple. You are giving the force. You are giving the force here. The compressive force you are giving. The sand is going here and there. How to avoid that? For that, we need to use mold box. We need to use the flask. The mold box and flask is the same thing. Just see this, mold box. It is known as mold box. This is known as mold box, or also we can say it is flask or flask. Now what is the material of that flask? Wood material. We can make this flask by the aluminum also, by the cast iron material also we can make. This flask has only sides. You can observe it carefully. No top. no bottom, it has only sides. And in that flask, we are putting our component, not a component, we are putting our pattern. Wood pattern we are putting here. The cubical shaped pattern I selected, that pattern, wood pattern I am putting there. And all the sides and on the top of pattern I am putting the sand and I am giving the compressive forces. I am giving the compressive forces. Very high forces I am giving, and because of that I am making the drag. The drag will get very, very high strength. The drag will get the good strength. Understood? Yes. This is very difficult to understand in only 1 hour session. Huh? This is not easy. To teach that procedure, I required 20 hours. In the 20 hours, you will get everything. But this is a just introduction. It is very difficult to explain in 1 hour only. Correct? Yes. Now see. Now here, and in this diagram also, I can show the flask. In that diagram also, I can show the flask. Just see, I am showing here. This is the flask I can show. Yes, I can show that flask. That wood material, that flask, that mold box is made by wood material or aluminum or cast iron. Just see it like that. Yes? Yes. Now this stage, we come up to this stage. How we come up to this stage? We inverted that. We inverted that. Just see, we inverted that. And here also I can show the mold box. It is in mold box only, but I am not showing mold box here again. Now we want a cavity. Now we want empty space there, casting cavity. How to obtain that casting cavity? How to get that casting cavity? For that we need to remove that pattern. Now I have very big question, how to remove that pattern? Just I can't hold it from anywhere. How to remove that pattern? From that we can use the spike. What is that spike? Just see, this is one of the metal or wood spike. In most of the cases we are using the metal spike only. This is known as spike. The spike has here the threads. The spike has threads like a screw. Then we can rotate the spike like that, and that spike, this tip will enter into the wood, and we can hold to that spike and we can lift it, and in that way we can remove the pattern. Why we are removing the pattern? To get the casting cavity. When we remove that pattern, we got here the empty space, and that is known as casting cavity. Here only I am writing the cavity. Here only I am writing cavity. This is the casting cavity. And now we produced here the drag of the mold box, the bottom portion of the mold box. In the same way, we can produce the cope also. Yes? Yes. Now see, here the drag, here is the cope, right? This is the cope. We can made by same procedure, cope also, and this is the drag. Now it's time to pour the molten metal. Now it's time to pour the molten metal. Now you can see the red color molten metal is there. We can pour up to this. We can pour up to this level also. We pour the molten metal into that. Now allow to cool that molten metal. How you can allow to cool that molten metal? Just wait for some time. Automatically the heat transfer will be there. How the heat transfer will be there? Here, if we are pouring the iron molten metal, we are pouring at 1700 degrees centigrade. Guys, the water is going to boil at 100 degrees centigrade, but we are pouring the molten iron at 1700 degrees centigrade. How huge temperature is there? And what is the atmospheric temperature? 20 degree, 25 degree, 26 degree. Then here I am writing the atmospheric temperature is 26 degree. Here the temperature is 1700 or below 1700. When we are pouring, then iron, we are pouring at 1700 degree centigrade temperature. But in the pouring process, the temperature of that iron is going to reduce continuously. Then here the temperature may be 1600 or 1650. And as the heat is going to transfer from here, the temperature of this molten metal is going to reduce continuously. And why there is heat transfer? Because of difference between the system and surrounding. The subject is thermodynamics. This manufacturing subject requires the knowledge of all other mechanical engineering subject. Here 26 degrees centigrade, here just consider 1500 degrees centigrade, and because of difference of temperature between the system and the surrounding, the heat transfer is going on. Wait for some time, then what happen? This will convert into the solid, this will convert into the solid. Yes, now see, it is converted into the solid. Yes, now we can see that here we got the solid component. Now also we can show it here. We will get like that solid component here. And when it will convert into solid, then we can break the mold. Break the mold means what? We can break the both cope as well as drag. We can break the cope as well as drag, and we can take out the casted component. Now tell me, what the shape of casted component we can obtain? Just see, first there was this type of pattern was there, cubical shape of pattern was there, and by using this cubical shape of pattern we made here one cavity. In that cavity we pour the molten metal. Hence, what is the shape of pattern? The same shape of casted component here we will obtain. And you can see that what is the shape of pattern, same the shape of casted component we will get. Now see, this type of casted component we will obtain. We will get this type of casted component. Now observe it carefully. Initially, the pattern dimension, how many? This is the cubical pattern, it has 6 faces. Each face's dimension, just consider it is a 12 centimeter. Each face dimension consider 12 centimeter. What is that distance? 12 centimeter. You can see that 12 centimeter, this pen distance is also approximately 12 centimeter. Then our each side of that cube is 12 centimeter. Just consider for the pattern, what will be the cavity size? The same will be the cavity size. Same will be the cavity size, that is only 12 centimeter. And in that 12 centimeter cavity size we poured the molten metal. It is converted into solid. Now it is also 12 centimeter. Now it is also 12 centimeter. Very important thing I am going to tell it here. Many of confusion I am going to clear here. Listen carefully. Pattern size 12 centimeter. Cavity size 12 centimeter. We poured the molten metal into 12 centimeter. Just consider one number 12 centimeter for understanding purpose. Because the casted component, different casted component we will manufacture. Now here it is also 12 centimeter. But now here 12 centimeter and we started breaking that cope and drag. But what happened now? I expected that this casted component must have a 12 centimeter size. But it is not true. It is never true. I got here 11 centimeter. This is 11, this is 11, this is 11, all sides 11 because we are studying the cube. But this all faces doesn't have smooth surface finish. We need to machining 1 centimeter from that all. And finally we got very small component of 10 centimeter size. Very small component of 10 centimeter size. That final component size is 12 centimeter. Final component size is 12 centimeter. Yes, good evening. I got some message here in the live chat. Yes, today there is a discussion on 2 important points, liquid shrinkage and solid shrinkage, as well as machining allowance, that we have to discuss in the today's lecture. Yes, now the question is that, I said it here, it is 12, but why casted component of 11 centimeter size I got? Then I did the machining and I got the final casted component of 12 centimeter, 10 centimeter size. Why the 12 to 11? Why the 11 to 10? This is the today's topic. Just see how beauty. Yeah, and for that you need to study the allowances. There are two main allowances which we have to discuss in the today's lecture. That first allowance is shrinkage allowance, the second is machining allowance, and these allowances are major allowances. These allowances are major allowances, and these three are minor allowances which we are not going to discuss in today's session. Now here, today's our topic is shrinkage allowance is our today's topic. Yes? Now see here, what is happening, just see the procedure in detail. We started pouring molten metal. Then we poured the molten metal here. You can see that we poured the molten metal here total. This is the full of molten metal here, full of molten metal. Then as this cavity is filled by molten metal, then what happened? The molten metal is also entering here. Molten metal is also entering here. What is that empty space there? What is that empty space? This is known as riser. This is known as riser. This is the part is known as riser is there. Riser. What is the riser? Riser is reservoir for molten metal. Riser is reservoir for molten metal. Yes, this is the riser. Some molten metal is entering into the riser also. Now see, we poured the molten metal. Then what happened? The shrinkage started taking place. Shrinkage, liquid shrinkage. Shrinkage means what? The reduction in volume of molten metal. Why the shrinkage started taking place? Here you can see that continuously the heat transfer is there, and because of continuous heat transfer, the temperature of that molten metal is going to reduce, and that liquid is going to shrink, means that volume of liquid is going to reduce. Volume of liquid is going to reduce, and that is known as liquid shrinkage, because liquid is going to shrink. The volume of liquid is going to reduce. Yes, and because of that, whatever the molten metal is going to reduce here, then the riser is supplying molten metal to that casting cavity. This is the cavity. This is known as casting cavity. The riser is supplying molten metal to that casting cavity. Some student can ask, sir, molten metal is also shrinking in the riser also. Definitely. But there is very big topic, that is riser design. In that riser design we are going to study that. The heat transfer area from the riser means we are using the cylindrical. This is the cylindrical riser we are using in most of the cases. And the surface area of that cylindrical riser must be minimum. Why it is must be minimum? If the surface area is more, then the heat transfer is also more. And if the heat transfer is more, then the riser will solidified before the casting cavity, before the molten metal in the casting cavity. And that's why we have to select such a dimension of riser. This is the diameter. This is the diameter of riser. This is the diameter of riser. This is the height of riser. We have to select such a diameter and height of riser. We have to select such diameter and height of riser that the surface area of that cylindrical riser must be minimum. If the surface area is maximum, then the heat transfer will be more. And because of more heat transfer, that liquid metal will convert into solid. And that will convert into solid before the molten metal in casting cavity. And that's why we selected the dimensions of riser such that it will solidify later. Means when firstly the molten metal in the cavity will convert into solid, and after then the molten metal in the riser will convert into solid. Hence, when there is shrinkage is going on, then this riser is supplying the molten metal. When the shrinkage is going on, then the riser is supplying molten metal continuously. And that's why you can see it here. Yes, in the diagram you can see. That's why the Here the 12 centimeter size is there, here is also same 12 centimeter size. Now you can ask me, sir, here riser is not shown. Yes, riser is not shown in that diagram, but hence the dimensions are not going to change. Still I said that here it is 12 centimeter, but when after breaking I got this 11 centimeter, why it so? And after machining I got 10 centimeter, why it so? That we have to see. Yes. Now see, for that we need to learn the stages of cooling in casting. But before the stages of cooling in casting, I want to tell you that what is the powering temperature here. The powering temperature is equal to melting point temperature of molten metal plus degree of superheat. Plus degree of superheat. This is the degree of superheat. This is the degree of superheat. This is the degree of superheat. What is meaning by degree of superheat? Some extra temperature we are giving to that metal. Just see, if there is a case of iron, if there is a case of iron, I am writing for iron, what is that powering temperature? For the iron, the powering temperature is equal to melting point temperature for iron. What is the melting point temperature of iron? It is 1539 degrees centigrade plus 150 to 200 plus 150 to 200 degrees centigrade. Then the powering temperature for iron is approximately equal to 1700. Means we are pouring the iron around 1700 degrees centigrade temperature. Now see next, for aluminium, what is the powering temperature? What is the melting point temperature for aluminium? It is 660 degree. It is 660 degrees centigrade plus 150 to 200 degrees centigrade. And then aluminium we are pouring around approximately 800 degrees centigrade. Now the big question, why we are wasting the energy? Why we are pouring the iron at 1700 degrees centigrade? Why not around 1600? Why we are giving the degree of superheat? If we are not giving the degree of superheat, then what happens? Just see in this diagram. We are pouring the molten metal, then as we are pouring the molten metal, continuously the temperature of molten metal is going to reduce. Continuously the temperature of molten metal is going to reduce, and you can see that molten metal is entering into the cavity. The molten metal is entering into the cavity. Molten metal is entering into the cavity. But if we are pouring at a less temperature, just consider for iron we are not pouring at 1700 degrees centigrade. We are pouring at only 1600 degrees centigrade. Then what happened? The flow passage, the solidification of molten metal happen in the flow passage. The solidification of molten metal is happened in the flow passage. Here the solidification of molten metal will be there. And if the solidification of molten metal is there, then you tell me how that remaining molten metal can enter into the cavity. It is not possible. It is not possible. It is not possible. Here the solidification is happened. Then the remaining molten metal can't enter into the cavity. Then whatever the volume of molten metal required in the casting cavity, we are unable to supply. That's why don't take risk. Don't take risk. And pour the iron at 1700 or any material, just this is the value 150 to 200 degrees centigrade. You have to give the extra temperature greater than melting point temperature plus 150 to 200 degrees centigrade. Now here we have to see the stages of cooling in casting. Just we'll take the example of iron here. At what temperature iron we are pouring? We are pouring the iron at 1700 degrees centigrade, and this is I am writing here. This is the first point here. I am writing the TP. What is mean by TP? That is a powering temperature. If we are considering the iron, then that powering temperature is 1700 degrees centigrade. You are pouring the iron at 1700 degrees centigrade. Then you can see in the diagram, on the x-axis there is a time, on the y-axis there is a temperature, and this diagram is the cooling curve for a pure metal. Cooling curve for a pure metal during casting. This diagram is not for alloys. Steel is alloy. In the iron we are mixing the carbon. then the steel is alloy. But here we can use this diagram for pure metals such as iron, copper, aluminum, we can use this diagram. Gold, we can use this diagram. Now see that at the first point the pouring temperature is there. As the time is going to pass, you know that the temperature is going to reduce and we will get up to this. And here is the temperature, freezing temperature. I am writing the freezing temperature TF. F stand for freezing, T stand for temperature. Freezing temperature, here TP. P stand for pouring, T stand for temperature. That is the pouring temperature. Correct? Now see that here I want to write some point, that is point A. Here I am writing the point B, and between the A and point, that is the first stage of casting. That is the first stage of casting I am writing here, the stage 1 of casting. Stage 1 of casting. Now at point A there is a liquid. At point B also there is a liquid, and this is the freezing temperature. Now there is very big question. What is the freezing temperature? Melting point temperature and freezing temperature are the same temperature. But whenever we are using freezing temperature, then the molten metal is cooling. And when we are using the melting point temperature, when we are supplying the heat, when the metal is going to melt, then we are using melting point temperature. When the molten metal is going to cool, when the liquid metal is going to cool, then we are saying it is as freezing temperature. Now this is the stage 1 in the casting. Then what is happening in the stage 1? What is happening in the stage 1? The metal is cooling from A to B point, pouring temperature to freezing temperature. And you can see that A to B, which heat loss is there? If you have the knowledge of thermodynamics, then you can see that there are two type of heat losses are there. One is sensible heat loss and second is latent heat loss. Sensible heat loss and latent heat loss. Here which heat loss is there? Sensible or latent heat loss? Definitely here the sensible heat loss is there. What is meaning by sensible heat loss? Temperature is going to change, but the phase remains same. Here it is liquid, but temperature is reduced. Why the temperature is reduced? Because of some heat loss, and that heat loss is known as sensible heat loss. That heat loss is known as sensible heat loss. Here is a sensible heat loss. Now see here the sensible heat loss is there. This is the stage 1 of casting. Here the sensible heat loss is there. I am writing here the stage 1. Which heat loss is there? Sensible heat. What is here? I am writing the sensible heat. Yes. And what is happening here? Here the material is cooling from pouring temperature to freezing temperature. The metal is cooling, molten metal is cooling from a pouring temperature to freezing temperature. Pouring temperature as a liquid to the freezing temperature as a liquid. That is what? Stage 1. Now what is happening in the stage 2? You can see that now we got stage 1, A to B point. Now see that C point I am writing here, C point, and here I am writing the stage 2. Now what is happening in the stage 2? At B point there is liquid, but at a C point there is not liquid. At a C point there is solid. At C point there is a not liquid, at a C point there is a solid. Yes. Then what is happening in the stage 2? Here is a freezing temperature. At a B point there is freezing temperature. At a C point is also there is a freezing temperature, and B to C, no temperature change, but the phase is going to change. Liquid is converted into solid, and that heat loss is known as, tell me, that heat loss is known as, when the phase is going to change, but the temperature remains same, that heat loss is known as latent heat loss, LH. That heat loss is known as latent heat loss. What is happening here? The liquid is converting into solid. How it's so? Just take one example. Just consider that at a B point, just consider, at a B point there is 1,000 drop of molten metal. Then at a B point out of 1,000, the first drop of molten metal is converted into solid at a B point. And as the waiting time is going to increase, as we are waiting here, then second drop, third, 10, 50, 100, at the middle point around 500 drop of molten metal will convert into solid, 600, 700, 800, 900, and at the last, at the end, thousands drop, 1000 drop of last number drop, 1000 drop will convert into solid. Means here what is happening? The liquid is converted into solid, and here this heat loss is known as what? Latent heat loss. And what is happening in the stage 2? What is happening in the stage 2? Yeah, see here the latent heat loss is there. Latent heat loss is there. Yes, how it is? The stage 2, in the stage 2, the shrinkage is happening from B point here. This is the B point as a freezing temperature as a liquid to the freezing temperature as a solid. Now say we completed here the stage 1 and stage 2. And guys, in the stage 1 and stage 2 there are some losses, means there are some shrinkage. The molten metal, shrinkage of molten metal is there, and that shrinkage is known as liquid shrinkage. That shrinkage is known as liquid shrinkage. Here you can observe that the liquid shrinkage. Here you can observe that the liquid shrinkage. This is the liquid shrinkage. Now see that liquid shrinkage means in the stage 1 is also shrinkage is there. Shrinkage of molten metal is there. In the stage 2 is also the shrinkage of molten metal is there. In both the stages the shrinkage of molten metal is there. Then my question is that if for the both stages it is there, then just see in the diagram, yes, then what I said here this size is 12 centimeter, cavity size is 12, this is also 12, but from when the liquid is converting into solid, there is a liquid shrinkage is there. Liquid shrinkage is there, then why here the size I said 12, here also I said the size is 12 only. And in that diagram, in that explanation, in that cooling curve, I am saying that the liquid shrinkage is there. The volume of that liquid is going to reduce. The percentage of liquid is reduced. Yes? Then, even though the percentage of some shrinkage is there, but the riser is there to provide the molten metal. Here you can see that the riser is providing the molten metal. You can observe it that here the riser will supply the molten metal. Hence, the 12 centimeter size remains 12. It will not change. Yes. And at the C point, at the A point also there was 12 size. At the A point also there was 12. B is also 12. At the C point is also 12. But when it will convert into the solid at C point, again you can see that the next stage is there. The next point is there. That point is D, and this is the stage 3. Stage 3 in the casting. At the C there is a solid. At the C there is a solid. At the D is also there is a solid. And C to D is also there is some shrinkage. And C to D is also there is some shrinkage. C to D is also there is some shrinkage. And when we are taking that casted component, yes, at the C point it will convert into solid. At a C point it will convert into solid. And what is about the D point? The D point, just see the D point. What is the temperature at D point? The temperature at D point is TR. R stand for room, T stand for temperature. This is the room temperature at D point is there. But C to D, cooling is there. But that cooling is not inside the mold. C to D, cooling is there, but that cooling is not inside the mold. Why it is not inside the mold? I said that we have to break the cope and drag and we have to take the casted component. Then stage 3 of cooling is happening outside the mold. At point C, we are lifting that cope and drag along with that casted component. We are putting on some vibratory mesh. Like that, this type of vibrations are given and the sand is started breaking and after the breaking we got the casted component. And when we started the breaking, then stage 3 is happening there only on the vibration mesh. Yes, and there the size of that casted component is changing from 12 centimeter to 11 centimeter. That numbers I am taking only for understanding purpose, only for understanding purpose I am taking that numbers. Hence the stage 3, what is happening in the stage 3, these C to D, the size is going to reduce, and that is known as solid shrinkage. That is known as solid shrinkage, because at a C there is solid, at a D there is a solid, and in between that the shrinkage is there. Hence we have to say it is solid shrinkage. It is solid shrinkage. It is solid shrinkage. Then here you got the two type of shrinkage. One is liquid shrinkage and one is solid shrinkage. And in both the cases, there is a shrinkage is there, volume is going to reduce, but no need to worry about the liquid shrinkage. Why no need to worry about the liquid shrinkage? Because riser is there to worry about liquid shrinkage. In the liquid shrinkage, whatever the shrinkage is there, same volume of molten metal supplied by riser. Yes, there is no need to worry about up to C point, up to stage 2, but after stage 2 there is stage 3. Here we are taking that all. Here this casted component, here this casted component cope and drag, and we are putting on vibration mesh and we are giving the vibrational forces, then the sand is started breaking and we will take that component. But when we take that component, we got 11 size of component. What is the size? Here we got at point D 11 centimeter. Why? Because of solid shrinkage. Because of what? Solid shrinkage. We got 11 centimeter size. And that solid shrinkage is also known as shrinkage allowance. Understood? That solid shrinkage is also known as shrinkage allowance. Yes, solid shrinkage is also known as shrinkage allowance. And just see here, this solid shrinkage is the shrinkage allowance, and today's the name of topic is also shrinkage allowance. Now the question is, what is that allowance word? Why that allowance word is used? Just wait and watch why that allowance word is used. Yes. Now just see about the shrinkage allowance. In which stage the shrinkage allowance is there? Stage 1 and stage 2. Tell me, is the volume of that cavity is going to reduce because of liquid shrinkage? In stage 1, 2? No. Whatever the volume is reduced because of shrinkage, same volume of molten metal is supplied by riser. This riser is supplying the same volume of molten metal here. Yes. Now see that very important point I am going to tell it now here. Whatever the material we are using for casting purpose, out of that the aluminum has highest liquid shrinkage, and that is around 7%. Aluminum has highest shrinkage, and that is about 7%. That is about 7%. Yes, I can say that the aluminum is shrinking largest in the liquid state, and that is very, very important theory question for any examination in India where the casting is given in syllabus. The aluminum has largest shrinkage allowance, and that is about largest liquid shrinkage, not shrinkage allowance. The aluminum has largest liquid shrinkage, and that is about 7%. We see if this cavity, just see, this is the, I shown here the diagram of cavity. Just consider if this is cavity of 100 centimeter cube, if the volume of cavity is 100 centimeter cube, then the aluminum shrinkage is 7%, then what will be the remaining volume of molten metal? 93 centimeter cube will be the remaining volume of molten metal. 93 centimeter cube will be remaining volume of molten metal. Now you tell me, this casting cavity requires what volume of molten metal from the riser? Riser must supply 7 centimeter cube of molten metal, at least 7 centimeter cube of molten metal to the cavity. then again it will reach to 100 centimeter cube. Means because of liquid shrinkage, even though the shrinkage is there, no need to worry, riser is supplying the molten metal. Understood? Yes. Then no need to worry about the liquid shrinkage. Riser is there to worry about the liquid shrinkage. Now see the little bit about the solid shrinkage. Just see that the solid shrinkage is also known as shrinkage allowance, that is today's topic. And this is the formula, that is change in length is equal to alpha delta TL. You can see that this is the same formula which students are using in the strength of material subject. Same formula is there. Alpha delta TL. What is delta T? Freezing temperature minus room temperature. Freezing temperature minus 2 room temperature into L, that is initial length of component. Where is the freezing and where is the room? Just see, where the solid shrinkage is going on. Solid shrinkage means shrinkage allowance. It is happening in the stage 3 from C to D. And what is the temperature at C point? TF. What is the temperature at D point? You can see the TR. Then this difference is what? TF minus TR. The difference is what? TF minus TR. And here we got the formula for delta L, change in length for solid shrinkage. Correct. Now see that solid shrinkage, you can see that the change in length is depend on alpha, or it is directly proportional to alpha. Yes, change in length is directly proportional to the alpha. Means this value of solid shrinkage is depend on alpha. And out of all material which we are using in the casting, out of that all material, the brass has highest value of alpha. And that alpha for brass is 23 into 10 raised to minus 6 per degree centigrade. Hence, I can say that this what is meant by alpha? Alpha is coefficient of thermal expansion. Means when take some metal, give the heat, it will expand. Why it will expand? Because it has a property, it has some coefficient of thermal expansion, and that coefficient of thermal expansion is different for different material. If we have to speak the value of alpha about the steel, then it will be the 13 into 10 raised to minus 6 per degree centigrade. As the material is changing, the value of alpha is changing. Right? And out of that all material, as we are giving heat to the solid component, and if that solid component is brass, then huge expansion is there. And when we are cooling, huge contraction is there. Here we are cooling from the point C to D. Here we are cooling from the point C to D. C to D we are cooling. I said that here the dimension at point C is 12. And for the cube, the dimension at D point is 11. I said that. The C to 11, 1 centimeter is there, change in length, that is contraction. All the size of cube, how many faces? 6 faces. All the size dimension is 11 centimeter. Yes, now see here. Then I can write that the solid shrinkage is highest in case of brass because it has highest value of alpha. Just see here, the liquid shrinkage is highest in case of aluminum. The solid shrinkage is highest in case of brass because it has high value of alpha. Now the next question is there, liquid plus solid. Liquid plus solid shrinkage. Liquid plus solid shrinkage is highest in case of which material? Now listen carefully. Liquid plus solid shrinkage is highest in case of steel. Highest in case of steel. That all are very, very important point for any examination in India. Aluminum has highest liquid shrinkage. This brass has highest solid shrinkage. And the steel has highest liquid plus solid shrinkage. Very, very, very important question is there. But still now there is a question, what is that allowance? Now see that what is that allowance here. Yes, firstly, this is the pattern size, and from that pattern size, what the pattern size we selected here? The 12 centimeter. Then we got the casted component of 11 centimeter. Then because of machining 10 centimeter. Now 12 to 11, the dimensions are reduced because of solid shrinkage, means because of shrinkage allowance. And this is reduced because of machining allowance. Yes. Now what is happening, if you are working in the casting company, they will tell you the dimension of casted component, and from that you have to design the pattern, you have to calculate the dimension of pattern. Then how you can calculate the dimension of pattern? See that. There is one best formula for to calculate the pattern size, just see the pattern size, then pattern size is equal to casting size plus or minus allowances. Here I don't want to write the minus, that is again the next part is there, only here I am writing plus casting size plus allowances. Now what is the casting size here? The 10 centimeter I am writing only CS, try to understand casting size, plus here is after casting size is 10 centimeter. After 10 centimeter we have to add the machining allowance, that is what, 1 centimeter, then I am writing here the machining allowance. After machining allowance we have to add the shrinkage allowance. After machining allowance we got this size of component. This means we are calculating, we are doing the calculation in our notebook. Casting size is 10, machining allowance, just see what 1 is there, and from that we will get 11 centimeter the component's pattern size, then machining allowance. Then from 11 centimeter to 12 centimeter, 1 will be the shrinkage allowance. Hence I am writing here the shrinkage allowance. Then casting size is 10, machining allowance is 1, shrinkage allowance is 1. Then what the size of pattern we can get? We can get the pattern size is equal to 12 centimeter. And in the casting company, you have to do that calculations. Yes, very tough part, not easy to understand. But here I tried to teach you in 1 hour. We have only the 1 hour time and I tried to teach that. A very important concept. And whenever my classroom student will ask, sir, I was absent for that lecture, I will send this video. And that is very great thing for the student. That's why only I selected this topic. Now again see, we will go and we will revise once it, what is happening here. Yes, this topic was there. Firstly we made, just once do the revision, pattern size. Just see the reverse process, we made the pattern, we have to make the casting. Pattern size is 12. Then we are producing the drag. Then here cavity size is 12. This is 12. This is 12. Up to C point, it is converted into solid, C to D. Break it. After breakage, what size of component we got? 11. And final casting is 10. Then what are the allowances? To calculate the pattern size, take the casting size that is 10 centimeter. Some machining allowance is required for good surface finish. And from C to D, that is third stage of casting, some shrinkage is there. The metal will shrink. The volume of metal is going to decrease. That's why also we need to consider one allowance. And that allowance we consider the shrinkage allowance. And that was the today's topic, shrinkage allowance. And in that way, finally, we can calculate here the pattern size. I hope so you understand this. Yes? Yes. And now our time is going to finish. Yes, again I will repeat this concept. Here the size was cavity size 12, 12, 12. Here we got 11. After 11 machining and we got 10 size. Right? Now see that in the liquid shrinkage, the stage 1 and stage 2 what happened? Shrinkage was there, but riser is supplied molten metal. Yes. Now here I am going to end this lecture now. And I want to say you all thank you for attending my lecture. And definitely I hope so this video will be useful for the student in future. If my classroom student is there, I am teaching that all part, but sometimes some student is absent, then I can give him this video and it will be better for student to revise. And I hope so this big part, tough part I tried to explain in 50 to 60 minutes only, and I hope so you understood that all the part. And finally again I am saying you thank you very much for attending my session. Thank you, bye bye, and all the best for your examination.
I am Nikhil Kumar Saha. I got AIR 1 in Gate Mechanical 2022. I was enrolled in ace.online test series program. So test series, whether it would be subject wise, topic wise or full length test, it helped me to improve my numerical solving skills in all the domain of the subjects that are included in mechanical. It helped me to cope up with the new numerical type of problems which normally students face difficulty in solving in first go. So it helped me to cope up with this type of numericals, and also I got to know through different multiple choice questions, multiple select questions which are now in the GATE mechanical they have introduced. So I got very good quality questions, so it helped me in preparation a lot. I am Nikhil Kumar Saha. I got AIR1 in GATE Mechanical 2022. I was enrolled in ace.online test series program. So test series, whether it would be subject wise, topic wise or full length test, it helped me to improve my numerical solving skills in all the domain of the subjects that are included in mechanical. It helped me to cope up with the new numerical type of problems which normally students face difficulty in solving in first go. So it helped me to cope up with this type of numericals, and also I got to know through different multiple choice questions, multiple select questions which are now in the GATE mechanical they have introduced. So I got very good quality questions, so it helped me in preparation a lot. I am Nikhil Kumar Saha. I got AIR1 in GATE Mechanical 2022. I was enrolled in ace.online test series program. So test series, whether it would be subject wise, topic wise or full length test, it helped me to improve my numerical solving skills in all the domain of the subjects that are included in mechanical. It helped me to cope up with the new numerical type of problems which normally students face difficulty in solving in first go. So it helped me to cope up with this type of numericals, and also I got to know through different multiple choice questions, multiple select questions which are now in the GATE mechanical they have introduced. So I got very good quality questions, so it helped me in preparation a lot. I am Nikhil Kumar Saha. I got AIR1 in GATE Mechanical 2022. I was enrolled in ace.online test series program. So test series, whether it would be subject wise, topic wise or full length test, it helped me to improve my numerical solving skills in all the domain of the subjects that are included in mechanical. It helped me to cope up with the new numerical type of problems which normally students face difficulty in solving in first go. So it helped me to cope up with this type of numericals, and also I got